Hello everyone, my name is Shubhang Garodia, Chemistry Master Teacher at Vedantu, and let us continue what we were covering in the last class. So guys, in the previous session we were talking about reaction mechanism. We discussed lots of questions where we saw application of reaction mechanism. We primarily discussed SN NGP, SNI in the last class, and today we are going to move ahead and discuss many more questions. So guys, when we talk about reaction mechanism, as I told earlier, the theory of SN1, SN2, E1, E2 comes to mind, but it's not just that much. Rather, what is more important is how we apply that theory while solving questions. Mechanisms are important. I'm not saying they're not. Why are they important? In multiple correct type, you can have many mechanism based questions. They can ask you order, they can ask you dependency on the rate and whatnot. But even if you don't know the mechanism, if your application part is very strong, if you know what that reagent does, how it behaves in presence of a given substrate, you should be able to solve the questions. Okay guys, with this, let us start with our very first question. Chalo. So this is the first question, guys. The question may we are given a alkene and we have been given a stereo center here. So this is a given stereo center. We want to react it with bromine CCl4 and we have the options whether it will form diastereomer, racemic, meso or pure enantiomer. Cool. Now, first of all, we need to understand what kind of addition is bromine addition. We know that bromine addition is anti-addition, right? How does it proceed through? It proceeds through cyclic bromonium mechanism, cyclic bromonium formation. Now, if you apply this, if you see this question properly, we have been given an alkene here and there is already a chiral center with a fixed configuration. Guys, please notice in the given question, CH3 is already given to you as wedge position substituent, right? That means the configuration here is fixed. I cannot change it. Now, what do you mean by anti-addition? Anti-addition means two bromine will get attached, one above, one below, right? So let's attach two bromine on the given compound. Let's see what do we get. This bottom carbon is fixed already as CH3 here, H here. Now when we attach two bromine, one above, one below, suppose I attach bromine above here, so bromine, another bromine will be below the plane as dash. Is this the only possibility? Huh? Can this be the only possibility? Absolutely no. I am sure many of you must have figured out there is one more possibility of adding the two bromines. This can be dash and this can be wedge. So bromine addition is an anti-addition, yes. So we added two bromines on the alkene, one above, one below, then we reversed it below and above. Now let's talk about the stereochemistry of the product formed here. So if we talk about the stereochemistry of the product formed here, we have three chiral centers now, 1, 2 and 3. Here also we have three chiral centers, 1, 2 and 3. Let me call it 1 dash, 2 dash and 3 dash. Let's compare 1 with 1 dash, 2 with 2 dash, 3 with 3 dash so that we can establish a relationship between them. If you check 1 dash, 2 dash are opposite of each other. 1 is opposite of 1 dash, 2 is opposite of 2 dash, but 3 is equal to 3 dash. The third stereo center that I have marked was already given to you in the question. So that is not getting affected during the reaction at all. Now, 2 are opposite but 3 is same. We can understand this by suppose if if this is R, this was R, then this is S because they are opposite. This is not going to be R, this will be S, so this will be R, the opposite of it. The thirds are equal, so let's say R and R. As you can see, opposite, opposite, but same. So this set is neither identical nor opposite to this set, the other set. The first set is neither opposite nor identical to the second set of configuration. Therefore, the two given compound are diastereoisomers of each other. Diastereoisomers are those compounds which are optically active, but they are not mirror images of each other. They are optical isomers, but not mirror images of each other. So the answer is diastereoisomers. Is this much understood, guys? So this was about addition of bromine on a pi bond, and one chiral center was already given to you. If you think you understood it, if you really understood it, let's try and apply it on the next question. Chalo, let's try and apply it on this given question, guys. So it's a similar question. We have alkene, we have a fixed chiral center, and we are adding bromine to it. The only thing that is changed in this question and the previous one is position of the pi bond. Theek. So let's start solving this question in the same way as we did the previous one. We'll add two bromines, one above, one below. Here it is already given to us as CH3 and H. Now I'm adding bromine, one bromine above, one bromine below. The first bromine can also be below, so the second bromine will be above. That means in the wedge. And the two parts, that is CH3 and H, was already a fixed configuration. Now let's try and establish relationship between the two. If you notice, these two are already mirror images. I have drawn them. They already appear to be mirror images of each other. Do they? They already appear mirror images of each other. Not exactly, right? Not exactly. Yahan pe we don't see mirror image with this. I completely agree with you. We don't see a mirror image here. But I'm sure you understand that this one is a mirror image of 1 dash. This 2 is a mirror image of 2 dash. Correct? And what is happening here? The configuration, just like the previous case, is remaining the same. Isn't it? So how do we approach this question? How do we develop a relationship between the two compounds, whether they are diastereomers, whether they are racemic, or whether they are optically pure enantiomer? Definitely this is not the answer because only two compounds were formed. Definitely this is also not the answer because we don't see any plane of symmetry in either of the structures. So we are left with racemic or diastereomers. Let's take a minute. Let's think about it, guys. Ki how do we conclude? Think. I'm sure you will get it. Are they really mirror images of each other? Yes, no. That should help you with the question. They are mirror images of each other. They are optically active compound and they are mirror images of each other. A wedge does not become a dash when we make a mirror image. A wedge does not become a dash when we make a mirror image. Imagine there is a mirror here, okay, and I am standing like this in front of, and the mirror is here. In the reflection also, you will see one hand going outside only. You will not see one hand going inside, isn't it? So what comes out, what is a wedge, remains a wedge in the mirror image. What is a dash remains a dash in the mirror image. The location would be different, that's it. So as you can see, these two are indeed mirror images of each other and therefore they are racemic mixture. The product formed is a racemic mixture because bromine will get added on this pi bond with equal probability in the first way and in the second way. There is no steric hindrance in a particular direction near the alkene. So bromine can get added from above as well as below with equal ease. So both of them formed in equal amounts. Both of them are mirror images. Both of them are optically active. So therefore they are racemic mixtures of each other. Very interesting question, guys. When you put this one and the previous one together, very interesting pair that can be asked in exam. I hope the concept is clear. Anti-addition of bromine on alkene, and there is a chiral center already present. Chalo, let's go ahead then. Now, this is a very simple, very easy, but a very interesting question. What does the question states? We have an alcohol, we react it with concentrated acid and heat, we get product and we have to judge the product. We know that alcohols undergo dehydration when you heat them with an acid. Alkene product should be formed. That is what we can see in the options as well. So let's start off with the question, okay? Now, in order to write or solve quickly, I am switching from atoms to bond line diagram. On the left, you have 4 carbons. So 1, 2, 3 and 4. Then you have your carbon which is attached to 2-methyl. So this is your given compound. Please check. Carbon pe you have a 4 carbon line. There are 2 methyls. There's a carbon and there's a OH attached. Now what happens when you put acid? When you put acid, this OH becomes H2O plus and it gets removed as water. So what do we expect? We expect a carbocation getting formed at this position. Now, we know that whenever a carbocation is formed, there are chances of migration. We can migrate the carbocation to a new position so that it becomes more and more stable. As you can see here, 2 groups are possible that can migrate. One is methyl group and the one is this 4 carbon N-butyl group. Which group migrates? When we talk about migrating tendency, let me just go to the next slide. Yeah. When we talk about migrating tendency or migratory aptitude, more electron donating system migrates first. If electron density is higher, then it migrates first or migration is faster. Okay? Therefore, we had 2 options, N-butyl and we had an option of methyl. Which one is more electron rich group? N-butyl is more electron rich group. Why? Because it contains 4 carbon. Right? So N-butyl will migrate first, not methyl. Let me go back. So here N-butyl group migrates, not methyl. Be very careful. In general, whenever we see methyl, we jump and we start migrating methyl. We know that migratory aptitude mein first is hydrogen, then is aryl, then is alkyl. Within aryl and within alkyl, more electron rich group migrates first. Be very careful of this fact. So, what happens? This N-butyl group migrates completely. Our carbocation comes into correct position. 1, 2, 3, 4, 5. Yeah. So 1 carbon was already here. This 4 carbon thing migrated to the right. You got a carbocation here. And then it will end up forming the alkene. Alkene will be formed such that it gives most stable product. It has most number of alpha hydrogen, ZF alkene. So can you match which option matches with this? Which option matches here? We want 2 carbons, then alkene, and then we need 3 more carbons. 2 carbon alkene, 2 carbon alkene, and then I have 4 more carbons. 1, 2, 3, 4. Yeah, 4 more. So that's B. I understand. We all know migratory aptitude. We have been practicing it from 11th standard. But then it is very important to understand this part, that within alkyl, more electron rich group the one that has more carbon atoms will migrate first. If you have aryl, the ones that have electron donating groups on it, those rings will migrate first. Okay? So, I hope this question is clear now, guys. We have also given you the printed solution. Incorrect statement about SN1 mechanism. In this question, they are talking about the mechanism of SN1, and if we look at the options, they're talking about racemization. They're talking again about racemization, inversion. That means the question is all about the mechanism of SN1, where we need to discuss racemization and inversion. So let's go first to the theory, then we'll come back to the options. Now, what happens in a SN1 reaction? I'll take an example where we have a chiral center with us. Suppose we have this as the given question. Okay? This has a chiral center here, 4 different groups are attached, and we have to react this with simple OH minus. Now, we understand that I am telling you that make this reaction undergo SN1. So, what do? We say that the given compound may say Cl minus goes away, generating a carbocation, right? And then we say that in the next step, OH minus attacks, giving your product back to you. First step is your slow step because a carbocation is getting formed. A reaction intermediate is getting formed. Now, please look at the challenge in this case. Your carbon or the chiral center is 2 degree in nature. It's not a 3 degree carbocation, right? It cannot form a very stable carbocation like tertiary butyl or phenyl carbocation or benzyl carbocation. This is not that stable in nature. So will it readily form carbocation? Will it easily give away the Cl minus group? Perhaps no. Also remember, OH minus is a nucleophile. This carbon has a del plus on it. If there is delay in forming the carbocation, this can undergo SN2 type reaction, isn't it? If there is a delay in carbocation formation, this can undergo a SN2 type reaction. See guys, these are molecules. They follow thermodynamics ke rules. They don't follow your and my theory where we say, no, you stand at a side, let him go and react. Doesn't happen that way. So we have a compound. Ideally, it should form a carbocation and then the nucleophile would attack. Correct? But what actually happens? The nucleophile doesn't wait for the compound to form a carbocation. If there is delay, the nucleophile will directly attack, making it undergo SN2 as well. So SN1 say, we know that inversion is done. We know that racemization takes place. How racemization takes place? Carbocation can be attacked from above as well as below. So we can get 2 products formed. One on the right, one on the left. Isn't it? So SN1 mechanism say we get these two 50-50 equal. And SN2 mechanism say we get this one. Oh sorry, not ClOH. SN1 mechanism say we get this one. SN2 mechanism say. So do you notice that overall you have one type of isomer more than the other? Do you notice you have one type of enantiomer more than the other? Because not only SN1 is taking place, but along with SN1, some amount of SN2 will always be there. So SN1 gives 50-50 RS. SN2 gives one type of enantiomer a bit. So overall, one type of enantiomer is more than the other. So not complete racemization takes place. There is slight excess of inversion. There will always be some SN2 happening with SN1. So there will be slight excess of inversion. Why is SN2 happening along with SN1? Because carbocation is not getting formed fast enough. This is not a very stable carbocation formed as an intermediate. Let's go back to the question. So the question says, in practice, the expected racemization is rarely observed. Correct. In practice, SN1 के साथ साथ there will always be some amount of SN2 happening. So not complete racemization takes place. The more stable is the carbocation, the greater is the proportion of racemization. Absolutely correct again. More stable carbocation, so more chances of SN1, lesser chances of SN2. So more amount of racemization will take place. The more nucleophilic the solvent, the greater is the proportion of inversion. See guys, when we talk about a substitution reaction, if the solvent can attack, the solvent will attack. As I told you, these are molecules. They don't follow your and my theory. They simply follow law of thermodynamics. So if there is one substrate, you added a reagent, but there is a solvent also which can attack. Solvent will also attack. Solvent go, I cannot keep aside, no, don't attack. If the solvent is a nucleophile, it will also attack. So that's what is happening here. The solvent can also attack, and if the solvent also starts attacking, more SN2 will take place. That's what it says, that if the nucleophilicity of the solvent is high, that means solvent is a better or a good nucleophile, SN2 starts dominating. If you remember, when we talk about SN2 versus SN1, here we need a poor nucleophile so that it doesn't attack immediately. Here we need a good or moderate nucleophile so that it can attack quickly and go for inversion, go for single step. So if solvent is also nucleophilic in nature, it will definitely attack and start giving you more inverted product. So this also seems correct to me. Racemization is very much less of a stereochemical requirement for SN1 than inversion is for SN2. English is complicated, but what it is saying is, it is summarizing the 3 points together. Ki if SN2 takes place, inversion is necessary. Inversion is compulsory. That's true as well. SN2 is a backside attack, so inversion is compulsory. But if we talk about SN1, is racemization compulsory? No. SN1 mein we just saw the theory here that SN1 mein racemization is not at all compulsory. Rather, along with racemization, we always get some amount of inverted product. I've just written this OH minus as a reactant here. Actually, it is not getting reacted. This was your SN1 pathway. ठीक. Going back to the options. Interesting question overall. SN1 ka racemization and how SN2 takes place along with SN1 getting discussed here. So what should you do in the exam? If they ask you a reaction is undergoing SN1, will there be complete racemization? Answer is no. Okay, there will always be some amount of inversion along with racemization happening. Chaliye, let's go ahead. Interesting question. Not exactly related to SN1, SN2, E1, E2, but addition reactions are also part of reaction mechanism, isn't it? Pura carbonyl, the entire carbonyl compounds chapter is revolving around such questions where you talk about aldol, canizaro, which are essentially addition reactions. So let's start talking about one. The question talks about cross aldol, and he has given some options here. Cool. So let's discuss cross aldol mechanism first. What do you mean by cross aldol? Cross aldol means two separate compounds are used for conducting aldol. I am selecting acetone along with formaldehyde. These two compounds I am using to conduct aldol reaction. Now, we know that aldol reaction has two mechanisms, base catalyzed or acid catalyzed. Right now I am discussing base catalyzed mechanism. So only this compound has alpha hydrogen Formaldehyde does not have any alpha hydrogen. So this compound acetone reacts with the base, forms a anion. What is the name of this anion? We call it enolate. It has a resonating structure, CH2 double bond C, O minus and CH3. So this is your enolate ion. This enolate ion then further reacts with formaldehyde. The anion here attacks, C double bond O goes here. So CH3, C double bond O, CH2, CO minus. The mechanism is the same, guys. If you had two acetone, you would have reacted them to give you aldol product. Similarly, now I have acetone and formaldehyde. Since formaldehyde does not have any alpha hydrogen, it's the acetone whose alpha hydrogen we used up. Now, next step, H plus heat. If I H plus heat, first I will get alcohol, which will get dehydrated to give me alpha beta unsaturated carbonyl. So as I said, product is also the same. Cross aldol means just we are using two compounds, not just one. Let's go to the question. The question says ketone was added to a solution containing aldehyde and base. Correct. In general, aldol ka yields are anyways poor. If you take two ketones, then one ketone can attack the other ketone can attack the first, and self-aldol is also possible. What I am saying here is, suppose I have acetone and I react it with acetaldehyde, aldol. So let me call this A and B. A can attack B, A can attack itself, B can attack A, and B can attack itself. Why? Because A and B both are ketones, both have alpha hydrogens. So both can form enolate and both can be attacked as well. So if I use such kind of a system for cross aldol, I will get lot of product. The yield of a desired product will be less. So therefore, in general, guys, when we do cross aldol, we take one ketone, one aldehyde, one with alpha hydrogen, one without alpha hydrogen, one which can form a enolate, the other which cannot form a enolate. Cool. Therefore, first option is correct. Ketone was added to a solution containing aldehyde and base. Can it be acid catalyzed? Yes, it can be acid catalyzed. We form enol and then we take the reaction ahead. We don't form enolate then. The electrophile is enolate. No. If you remember, enolate attacked. Enolate attacked. It was a nucleophile. The carbonyl compound was an electrophile where the enolate attacked. So enolate is a nucleophile and your carbonyl was a electrophile. I'll show you the mechanism. Enolate attacked the carbonyl which had del plus. So this is your electrophilic center. This is your electrophilic center and here you have negative. So this is your nucleophilic center. So this is wrong option, not matching. This is correct. Last, aldehyde is used in excess. Aldehyde is used in excess. Yes, that is also correct. Let me show you. Let me write and clear it for you. Now, here there was also a possibility that acetone reacts with itself to give aldol. Acetone reacted with itself to give a self-aldol product. Right? That was also a possibility. The question said we want to conduct cross-aldol. We want the enolate to attack formaldehyde. We don't want the enolate to attack acetone again. Take formaldehyde in excess. If I take formaldehyde in excess, enolate ion will see more formaldehyde molecules around it, lesser acetone molecules around it, so it will preferably attack formaldehyde molecules. That is why your question mentioned that aldehyde is used in excess. Correct. Why? To reduce the amount of self-aldol. Clear? So in this question we learnt about cross-aldol reactions. What are the things to take care if you want high yield of cross-aldol reaction? Take aldehyde in excess. Don't use two compounds having alpha hydrogen. Use one with alpha, one without alpha. And yes, we can conduct an acid as well as base catalyzed mediums. Isn't it interesting कि how a simple aldol reaction के questions can be so theory or thought provoking? चलिए, let's go ahead. This is also pretty interesting question. A very simple but an interesting one. The question says, the reaction of Q with PHSNA yields an organic compound and that organic compounds give positive Carius test with barium chloride. What is the compound Q? So these are the four options given for Q. We have to react Q with PHS minus Na plus. Looks like this is a nucleophile. And then the product gives what? The product gives positive Carius test for barium chloride. If you remember, positive Carius test for barium chloride means positive test for sulfur. Why? Because barium chloride reacts with the sulfate forming barium sulfate. How will we get sulfate? Na2O2. In the first step, we react Q with Na2O2. Na2O2 is an oxidizing agent. It's a peroxide, so it's an oxidizing agent. Sulfur present in your Q gets converted to sulfate. And then we further react it with barium chloride. So we get white precipitate here. Insoluble in acids. That means he is, not Q, Q dash. So that means Q dash should have which element present in it, guys? Q dash should have sulfur present in it, isn't it? Where will the sulfur in Q dash come from? It comes from PHS minus. PHS minus, say the sulfur in Q comes into picture, which then gets tested in barium chloride method or Carius method. So let's go back to our question. PHS minus is a nucleophile and we have been given organic compounds with electron withdrawing groups on it. So I'm sure you understand we are looking at nucleophilic substitution in aromatic compounds, right? NO2 being a electron withdrawing group increases the reactivity. But when does NO2 increase the reactivity? NO2 increases the reactivity when NO2 is present at ortho or para position. NO2 increases the reactivity, yes, but when it is present at ortho or para position. So in the first case, guys, this F can easily be substituted with SPH because it is at ortho and para position. Here iodine is at meta, so this will not react. Compound C में there is NO2 but at meta position, okay? So this will definitely not react. And the compound already contains a sulfur. Be careful, compound already contains a sulfur atom. Next, if you have NO2 again attached at para position, but ये Cl तो can get easily substituted, na? This is outside the ring, no problem anyways. We can easily substitute it. A simple SN2 type reaction can take place. SME and SPH. So, except for your compound B, in which substitution cannot take place, in which there is no sulfur present already, my three compounds A, C and D all will give the test. A may NO2 is present at ortho and para, so I can substitute and bring SPH. C may there is already a sulfur present. D may there is already a sulfur present and we can substitute this Cl as well. So the answer here, guys, is A, C and D, where PHS minus can attack and either come into the picture or there was already a sulfur present in your given compound. Thick. Simple question, not complicated, but we must understand why is he talking about barium chloride or why is he talking about Carius method. Now, the very integral part or very important part of SN1, SN2, E1, E2 is understanding when to conduct elimination, when to conduct substitution. There's a very simple logic for such kind of questions. Whenever you have a 3-degree alkyl halide and I react it with a nucleophile, this is always a recipe for elimination. Whenever we have a 3-degree alkyl halide and we react it with any nucleophile, this is the recipe for elimination. Substitution does not take place in such situations. Okay? So let's look at question option by option. First one, you have a nucleophile and you have a 3-degree alkyl halide. We have a nucleophile and let me get some space. We have a nucleophile in the first question and a 3-degree alkyl halide here. So 3-degree alkyl halide, when a nucleophile attacks, what happens? We get elimination reaction. It proceeds via E1 elimination. Okay? This HBr gets eliminated and we get alkene formed as a product. Let's look at option number Q. In option number Q, we have a nucleophile and we are reacting it with HBr. This does not look like simple SN2. It is not. This is your ether hydrolysis. This is reaction of ether with HBr. So the side, there are two sides to your ether. One is this side, one is this side. The side which can give more stable carbocation breaks away. The side that can give more stable carbocation breaks away. So this side, the left side, can give you more stable carbocation because it's 3-degree. So left side breaks away, goes and attaches itself with bromine, and the right side, OMe, remains as it is. I'll just draw it again here for you. OMe, first step mein H. This gets formed, the oxygen takes up H+. Then in the next step, Br minus attacks, but your left side can form stable carbocation, so it automatically separates away, and then Br minus attacks here. So this is your product. Please notice there is a difference between the first and the second. First one was direct SN reaction, which in this case converted to an elimination because it was a 3-degree alkyl halide. But the second one is what? The second one is ether whose hydrolysis is taking place. Next. In the next question, we again have a 3-degree alkyl halide and a nucleophile OMe minus. 3-degree alkyl halide undergoes E1 elimination to give alkene. Let's go ahead. Next question. Here we have a 1-degree alkyl halide and we have a big nucleophile. If a nucleophile is big or bulky, it prefers elimination, yes. But here if you check, you have a 1-degree alkyl halide, elimination is just not possible. So a simple substitution takes place. Williamson ether synthesis is what you call this reaction, isn't it? So a simple question overall, guys, but challenging if comes in the form of match the column. So let's try and match our options. Now, in the first case, just a second. In the first case, what did we get as the product? It was a 3-degree alkyl halide, so we got alkene as a product. So definitely 4 got formed and this took a hydrogen. So 1, 4 is the answer for the first one, 1, 4. Here what happened? Here we got a 3-degree alkyl halide and methanol. Remember, ether hydrolysis was this. So what is the answer in this case? Only 2 is the answer in this case. Next, 3-degree alkyl halide, again alkene getting formed and methanol along with it. Methanol is not an option, alkene is the option here. So fourth, Williamson ether synthesis, the product is ether, matches with our third. So this becomes the answer. This is your answer set, guys. 1, 4, then 2, then 4, then 3. S. B. Bombay. We get very, very confused, very lost in the exam in such questions because we look at options. I did not look at the options. I simply solved it as a question and then matched the option. I know this will take slightly longer, but it will be absolutely correct method. You will not make mistakes. ठीक? So whenever you get a mechanism-based matrix type question, please solve it and then match options. Don't go for option elimination directly. That may not help you in JEE Advanced. Chalo, let's look at one more similar question. He says we are given the reaction sequence. Now we have to identify the reagent that we have to get. Reagent that is used. Okay. This has to come from outside. And O minus is already there. Ether is formed as a product. So it is very, very clear that this is Williamson ether synthesis. We can use ETBR and attack can take place on ethyl. Bromine will go out. Simple. This is your 3-degree alkyl halide. 3-degree alkyl halide se we want to make alkene. That means we want to conduct elimination. That means we would use a nucleophile or a strong base. Where do we see a nucleophile? We see a nucleophile here. So therefore, ETO minus, if I use, that is alcoholic KOH, this will attack and elimination E1 will take place. We have alkene and alkene pe we have added ethanol. Alkene pe addition reactions takes place in the presence of a catalyst generally. That catalyst is acidic hydrogen and we want to add ethanol. So ethanol and acidic hydrogen both are present here. So that's R. First ka answer was Q, second ka answer was P, this is R. Last. ETCl getting converted to butane. Ethyl chloride has 2 carbons, butane has 4 carbons. So 2 ethyl chloride have combined together. 2 ethyl chloride have combined together. That's your words reaction. We need active metal, isn't it? So active metal wala option is this. Therefore it is S. Now it's a simple question, guys. But if options are not given in the exam, this might become very tricky and very challenging for you to solve. Okay? So please have your concepts clear as to what is happening. Don't just try to mix and match the options. You might not be successful. So be careful. Avoid mix and match options. Avoid solving matrix match by option method in JEE Advanced. Try to solve them properly. Next. Very interesting question. Slightly complicated, slightly convoluted, but very interesting. He is given us the reactant and the reagent and he's asking number of stereoisomers now formed as a product. Think about it, guys. He says we want to conduct E2, specifically E2. We cannot conduct E1. That is very clear to us in the question. Okay. E2 elimination में carbocation is not formed. E2 elimination में rearrangement or migration does not take place. We simply form alkene as product. So if I have to solve option A for you, we have 4 carbons. 1 alkene can be formed on the left and 1 alkene can be formed on the right. Now, यहाँ पे this can show cis as well as trans. Here this alkene cannot show any geometrical isomerism. Why? Because the two hydrogens are present on it. The groups are same. So in first case we get 3 products formed. two pentene, which can be cis 2 pentene, trans 2 pentene, and 1 pentene. So total 3. Let's talk about the B case. In the B case, I will get only one alkene, whether you form it on the right, whether you form it on the left. But this alkene can show cis as well as trans, can show geometrical isomerism, and therefore the product formed are 2. One cis, one trans. Next. HBr gets removed. From here we remove H, HBr. From here we removed H, HBr. So here when you remove HBr, you get a terminal alkene. Terminal alkene do not show geometrical isomerism, so answer is 1. Now the next one. For E2 elimination, carbon carrying the bromine ka alpha carbon, this one, should have a hydrogen attached to it, isn't it? HBr gets removed in E2 elimination, so we get an alkene. If you notice, there is no hydrogen attached here. The carbon is already having 3 methyl groups. There is no hydrogen attached here. So this compound definitely cannot undergo E2 elimination. Question specifically says E2. So this compound cannot undergo E2 elimination. So products formed due to E2 elimination are 0. I am not saying no reaction will happen. Reaction will take place, not via E2 mechanism. So this is just the same thing repeated again, guys, showing all the compounds. Let me talk about the last one now. This was your last compound and alcoholic KOH was given to you. Although this compound cannot show E2, it will end up showing E1. Whenever there is 1 degree or 2 degree next to 3 degree, then it ends up showing E1 or SN1 type reaction due to stable carbocation formed after rearrangement. Let me show you. So now we have to make it undergo E1 type reaction. So Br minus goes away and a carbocation is formed. This carbocation can further rearrange to give a more stable carbocation, and then elimination or alkene formation takes place. So this reaction, this compound does react, but via E1, not via E2. Interesting, isn't it? We always mug up 1 degree halides undergo SN2, E2, but this one no. 1 degree halide, when it is next to a 3 degree carbon, it undergoes E1 या फिर SN1. Rest options were fairly simple in this question. Next, the number of hydroxyl group in Q is, we are given a compound H plus heat, then aqueous KMnO4. Alcohol pe, if I am using H plus heat, that means it's a dehydration reaction. That means water will have to be removed. This is our given compound, right? We removed water, we got a carbocation there. Why did we make a carbocation? We just now covered this. That 1 degree, 2 degree next to a 3 degree position undergoes SN1 या E1. Methyl migration takes place, I get more stable carbocation. And since heat is given to us, H plus will be removed, forming a alkene. Which alkene? ZZF alkene or more stable alkene. Now you have 2 alkenes. Okay. Aqueous dilute KMnO4. What does aqueous dilute KMnO4 do to an alkene? When you have aqueous dilute KMnO4, it converts the alkene to a diol. 2 OH gets added on nearby carbon atoms. So if you have an alkene, this gets converted to a diol. And is this anti-addition or syn addition? These are cis diol forms as product, not anti, not opposite. So let's take it ahead. I react this further. OH, 2OH. Now, it's not necessary that both the alkene के OH are on above side only. These two OH have to be on same side with respect to each other. These two OH will have to be same side with respect to each other. Is it necessary that both the OH of both the alkenes are also on the same side? No. What I am saying is, this is also a possibility as a product. This is also a possibility as a product. I used KMNO4, I added both the OH on one alkene on the same side, but on the other alkene it can very well be on the other side. So we will definitely get two products, but both of them contain 4 OH only. If both of them contain 4 OH only, that means answer is 4. He is asking number of OH groups in the final product. Very interesting question. They could have modified this question a bit and asked number of hydroxyl group in all the products which are Q. Total number of hydroxyl group in all isomers that are formed as the product Q. So you have two isomers formed as product, this one and this one. So then the answer would become 4 plus 4, 8. Okay, interesting question, but a simple one, not at all complicated. Very dangerous looking question. The given question says we want to find the number of aromatic compounds obtained when we conduct acidic hydrolysis of this. When we conduct acidic hydrolysis of this, number of aromatic compounds formed. Now guys, if you remember, RCl ka when you conduct acidic hydrolysis, it forms ROH. This can undergo SN1 if R plus is stable, and then simply water attacks. So let's try it in our compound also. Do we see R plus? Do we see leaving groups? I think we do. I think we do. Yeah. Now, this part of the compound, if separates away as a positive charge, this part of the compound, if separates away as a positive charge, this part of the compound, if it separates away as a positive charge, what do we get? We get tertiary butyl carbocation, which is stable. We get methyl cyclopropyl carbocation, which is stable. We get troponium ion, which is very, very stable. Right? So this compound is a very special case. Although it does not have direct leaving groups attached, when you put it in water, when it undergoes acidic hydrolysis, it automatically breaks and gives these 3 carbocations. What happened to the center part then? What happened to the big molecule or the big ring? 3 double bond O's were already attached on the big ring. Because plus charge left from the ring, they will get negative charge. Now, if you make tautomer out of it, or if you simply resonated them, that is, it underwent tautomerism, what will you get? We expect the system to become aromatic. Why did it convert from this to this? To gain aromaticity. So overall, if you notice, we have one aromatic product, we have second aromatic product. So 2 compounds are formed here as products which are aromatic in nature. So guys, this was it for today's class. I hope you liked the questions. I hope you learnt a lot from the questions. We will continue solving more such questions in the next class, and then we'll move ahead to the further topics. Thank you so much for joining, guys. Please do like, share and subscribe. Take care. Bye-bye.